Hello everyone, in this video I'm going to be talking about the addition reactions of alkenes and alkynes, and I'm going to be comparing those side by side so that you can see the differences in their reagents and what type of products they're going to be making. Now keep in mind, I'm not going to be talking about all the addition reactions of alkenes. That's because alkenes do more addition reactions than the alkynes. I'm only going to be talking about the ones that has a side-wise comparison between the alkenes and alkynes. So let's start out with this halogenation. So in case of halogenation, you will have an halogen added in the presence of carbon tetrachloride. That's just using as a reagent. So as far as your halogens go, you could use either Cl2, you could use Br2, and even you can use I2. But the two most common ones that are typically used is the chlorine and bromine. So the conditions for both the alkenes and alkynes actually stays the same. So let's see what happens in case of alkene. I'm going to make this a little bit smaller. So in case of alkenes, you add two halogens onto those double bonded carbons anti with respect to one another. So let's say if I duplicate two of those here, so I would have two products, and in each case you could have one chlorine coming out of the page. That means the other one will be going back in the page. So that top methyl will be pushed back in the page like this one. And in the second case, I would have the enantiomer of that basically. I could have that top chlorine going back in the page, and that would push this methyl coming out of the page, and the bottom chlorine in that case would be coming out of the page. Is make sure they are anti to one another in terms of the additions. So that's what you do in case of an alkene. Now remember, you only have to worry about the stereochemistry if they are chiral centers, and in this case they are chiral centers, so you want to make sure you're showing those opposite to one another. In case of an alkynes, similar things would happen. You're actually going to be adding the chlorines onto those double bond or onto those triple bonded carbons. The problem with that is it gets added twice. So I would have in the first step, you would go ahead and kill one of the pi bonds, and that would have the chlorine added. So obviously still going to be anti, but you can't really isolate that because as soon as this is made, the second pi bond will react with the remaining chlorine, and as a result, you would make a tetrahalogenated hydrocarbon there, something like that. So you would have four chlorines attached to those carbons in that case. So to kind of make sure this reaction goes to the completion, you use either two equivalent of the chlorine, or you may see people writing it as an excess. Because even if you use one equivalent, you will get a mixture of this middle intermediate and the product, so that's usually not useful. As a result, you want to go ahead and make sure you use excess chlorine so that you can get a tetrahalogenated alkane here. Now remember, the stereochemistry here is not going to be that important because you don't really have any chiral centers, even though those chlorines will be added anti to one another, but since there's no chiral center, we don't really have to worry about it. So that's really the difference in case of the halogenations when it comes to alkenes and alkynes. Let's talk about the next one. I also have hydrohalogenation. So in case of hydrohalogenation, we obviously going to be adding a hydrogen and an halogen. So typically you may have seen this being written as an HX where your X could be chlorine, bromine, and iodine. So any one of those three would work fine. In case of an alkene, so when I run this, suppose with an HCl in this particular case, it goes through the formation of a carbocation. Now remember, anytime you're making a carbocation, you will have a possibility of rearrangements. But here, I'm not really going to be showing the mechanism, just kind of briefly talking about what you're going to be making at the end of the day. So you have the hydrogen being your electrophile here, and your chlorine eventually going to be the nucleophile that's going to attacking the carbocation. You do this addition with respect to Markovnikov's addition. So your hydrogen goes to the bottom carbon here, and your chlorine will go onto this top carbon here. Now, remember this is Markovnikov's addition. This is going through carbocation formation, and because of that there is possibilities of rearrangements, but this one wouldn't really have any rearrangements. If I want to make sure this undergoes anti-Markovnikovs, I could do so, but I would have to use HBr in the presence of an hydrogen peroxide, or you can also call that to be ROOR. So that's going to be anti-Markovnikov. So what would happen in that case? I would have the bromine here. So remember, the anti-Markovnikovs typically works with the HBr. It doesn't really work with an HCl and HI. So this is what you're really going to get. You're probably going to get a multiple stereoisomers here because you can have bromine coming out of the page because you have multiple chiral centers. So I'm not really going to show that. You get a chiral center here, you get a chiral center here. So you have at least two chiral centers. So you could, possibly get a mixture of stereoisomers, most likely four stereoisomers. So that's something I don't want to really show, but just keep in mind this is going to be the anti-Markovnikov's addition. All right, and this doesn't really go through the formation of carbocation, but rather this goes through the radical mechanism that you usually learn whenever you talk about free radical halogenation. Now let's talk about what happens in case of an alkyne. You would still do something similar. I would be adding those either Markovnikovs or anti-Markovnikovs. So suppose what happens in case of Markovnikov. So let's suppose I do this in the presence of HBr. So in the first step, I would have the bromine added onto the second carbon because I want to make sure I do Markovnikov's addition and your hydrogen goes to the terminal carbon. But this doesn't really stop here, and in that case, your second HBr will go in and have this bromine added again onto the second carbon because we still got to do this Markovnikov's addition. So this is one of the ways you can make so-called geminal dihalides. And remember, this is still going to be Markovnikov's addition. Now, this is usually the intermediate in the middle that you make usually is not isolated because even though it goes through the formation of the intermediate, you cannot really retrieve it because as soon as this is made, you will make this final product, which is going to be your geminal dihalide. So remember, this is going to be the final product in that case where you're going to be adding two bromines and two hydrogens. But sometimes they may write down two equivalents of an HBr here, or they may write down in excess of an HBr. That's something you want to keep in mind. You could also run this anti-Markovnikovs, and to run this anti-Markovnikovs, I would go ahead and use HBr with H2O2. So I would it goes through the formation, obviously, with addition of only first one Br at a time. So you would have the bromine anti-Markovnikovs added here, and then it doesn't really stop here, and eventually the second you can also have ROR. The second bromine comes in from the HBr, and you would have this final product made. That's still going to be geminal dihalides, but it's going to be anti-Markovnikovs with respect to one another. So remember, you're always going to be making the final product, and this is going to be your final product here. It goes through the formation of that intermediate, but you can't really isolate it because it goes quickly to make that. Even if you use one equivalent of HBr, you will get a mixture. So you rather use at least two equivalent, or you may see it's going to be written as an excess. Okay, so that's your hydrohalogenation. Let's look at the hydrations. Now, hydration is a little bit interesting when it comes to both alkenes and alkynes. You could actually run three different types of hydrations for alkenes, and I would say two types of hydrations in case of alkynes. So let's talk about all of them. So in first case, it's going to be your acid catalyzed hydration where you would have H3O plus. You also we'll see that written as H2O and H plus. This is just in a simple H plus is being written used as an electrophile. It goes through the formation of carbocation. it still do Markovnikov's addition, however. So remember, if it's going through carbocation formation, you have a possibility of carbocation rearrangements in this particular case. But we don't have to worry about carbocation rearrangements here because it will not do any of them. So you have an alcohol made with the Markovnikov's addition. And remember, this goes through the formation of carbocation. Now, the second thing that you can typically do is called an oxymercuration demercuration. So in the first step, you use mercury acetate, and you could use water or alcohol depending on whatever you try to make. And then in the second scenario, you would use some sort of reducing agent. That's typically going to be the NaBH4. Now this still does Markovnikov's addition, so that's going to be very similar to the top one, but the only difference that you really have between this acid-catalyzed hydration and the oxymercuration demercuration is you typically don't see any carbocation rearrangements because you don't really make any carbocation in this particular case. So no carbocation formation for this one, so no rearrangements. That's the That's the advantage of using oxymercuration demercuration over the acid-catalyzed hydration. Other than that, they both give you Markovnikov's addition. It's just that it avoids any possibilities of rearrangements, whereas the acid-catalyzed will have a possibilities of rearrangements if there is one possible. Then you can also do the third one, and the reagent they typically use is BH3, THF, and then you can use in the second step would be H2O2 and some sort of base OH minus. Now remember, anytime you use H2O2, it's going to be doing anti-Markovnikov's addition, and that's what's really going to be happening here. So this right here, instead of the OH going down here, the OH actually going to be coming down here. So that could be coming out of the page. Now remember, this is an syn addition. The other two, like you have a possibilities of making an anti-merge if there is a chiral center. But for this one, since this is going to be a syn addition, and you got two chiral centers now, I would have this methyl being pushed out of the page, and this hydrogen will be coming out of the page. So that's your one possible product. And your second possible product would be the otherwise, where you could have these coming out of the page, or going back in the page rather. I don't really have to draw the hydrogen, but I'll just show that both hydrogen and the OH are added syn to one another, and that would push this methyl coming out of the page. So remember, this does anti-Markovnikovs, and in addition to that, it will have a syn addition of H and OH with respect to one another. So that's what you really see in case of hydrations for the alkenes. Let's look at what's really going on with the alkynes. So as far as the alkynes go, you're going to be seeing only two types. You would have the oxymercuration, well, it's kind of similar to the oxymercuration, but you still call it acid catalyzed. Instead of using mercury acetate, you use mercury sulfate and typically use sulfuric acid with water. So this is still going to be Markovnikov's addition, and the intermediate that you make in there, you kill one of the pi bonds, so the other pi bond is still going to be there. So your hydrogen goes to the terminal carbon, and then your OH goes to the middle carbon according to the Markovnikov's addition. So this actually makes an enol, but this doesn't really stay there, but rather it will tautomerize to a keto form. So this would be your final product in that case. That's your keto form, and that's more stable in that case, and that would be the most final product in this particular case. But when it comes to, let's see, the oxymercuration demercuration type reaction here, The reagent that's going to be slightly different. You may see BH3 being used in a lot of books as well, but a lot of time you may also see like instead of BH3, they may write down BBN, or they may write down something like even BH3 or even BR3. So all of those things are possible, along with obviously the THF here, and then your second. Um, reagents would be the same, the H2O2, and then you would have an OH minus. So that doesn't really change. This will add the OH just like we have been adding anti-Markovnikovs. So I would have the OH added kind of right here, but then this still going to be in an enol form, and it will actually tautomerize to in a keto form, and in this case it would make an aldehyde rather. So this is making an aldehyde at the end of the day. So the top one was still Markovnikov's. This bottom one is an anti-Markovnikov's. So that's the difference in what type of product they're going to make. In case of alkenes, they typically make the alcohols. Depending on the reagents, typically use water or an OH minus. You could make alcohols anti-Markovnikovs or Markovnikov's addition. In case of alkenes, you end up making either a ketone or an aldehyde that still goes through the process of them being either Markovnikov's addition or anti-Markovnikov's addition. Okay, so that's your hydration. Let's move on to the next one. Okay, I got the hydrogenation here. Hydrogenation is actually more interesting for the alkynes. Let's just talk about what happened in the case of alkenes. Typically, we would use H2 with palladium carbon, and it will just add two hydrogens onto that. And it's just literally going to kill that pi bond, and you're going to have two hydrogens added there. I'm not really going to show that. But one thing you do want to know that the hydrogens that are added here are going to be syn to one another. So it's an syn addition, even though there's no chiral center form, so I don't really have to worry about the stereochemistry. But remember, the hydrogenation of alkanes is indeed an syn addition. What happens in the case of an alkyne? So alkynes is actually an interesting one where you could be making different types of products. So if I'm using just a regular H2 with palladium and carbon, in the first step, I would actually make an alkene. But these alkenes are not isolated. You cannot really retrieve them. So at the end of the day, it actually goes through the formation of an alkene. At the end of the day, we'll actually make an alkene. So that would be your final product. Now, the question would be, well, is there any way we can stop this reduction at an alkene? And the answer is yes. You just have to be a little bit selective with what you're going to be using as your um, reagents here. And in one case, you can use something called PD with BaSO4 H2, and it sometimes also called the Lindlars. And you may also see being CaCO3 being used in that particular case. So this actually has the potential of stopping this reduction at an alkene, but then also in addition to stopping this at an alkene, it also makes an cis alkene. So that's another important thing you want to make sure you know. So it stops it at an alkene, but not only that, it typically makes an cis alkene as your major product. Now, then you may wonder, well, is there a way to make an trans alkene? And then the answer is yes, you can make an trans alkene. You just have to use a slightly different reagent. You can use liquid ammonia and sodium metal. So when you use that, it would stop the reduction at an alkene, but then on the top of that, it would actually make trans alkene. So that's a very important thing that everyone should know in sophomore organic chemistry. So that's how That's really the difference you're going to have in case of the hydrogenation between the alkenes and alkynes. Let's look at the next one, which is the ozonolysis. So the ozonolysis is kind of interesting for both of them, I would say. It's typically an oxidation. You could go ahead and use O3 in both of those cases, but then in the second reagent, whether you're doing an oxidative workup or a reductive workup, it's going to be slightly different. I could use H2S here, or something like zinc here. What it really does, it actually cleaves on a double bond. So it breaks up that double bond, and I can go ahead and number those carbons just for my own sake. So I could call this 1, 2, 3, 4, 5. So when you cleave this, you actually have now an open chain. So I would have 1, 2, 3, 4, 5. So you have 5 carbons there. So if I call this to be 1, 2, 3, 4, and 5, remember 1 has the methyl attached. So this methyl right there is going to be that methyl. So keep track of your carbons. And then you're going to have an O there. So that makes it a ketone. And number 5 also going to have an oxygen there. That makes it an aldehyde. So that's an important thing that you want to make sure you can keep track of it. If you, however, do this same reaction, but you do this under oxidative workup. So what's going to be really the difference? You have the O3, but instead of H2S or even like CH3 2S, you actually have an H2O2. So that's your oxidative workup, and the top one was the reductive workup. So this oxidative workup actually converts the aldehydes to an acid. So everything else will stay the same. You can't really convert your ketone to an acid, but your aldehyde right here on carbon 5 gets converted to an acid. So that's really the difference in that particular case. Now, what happens in case of an alkyne? It's kind of similar. We're going to be using an O3 again, and typically use water with it. You will break this pi bond, in this case, this triple bond here. So you will break that. And in either case, you make carboxylic acid. So that's really the difference. Okay, you would have the acid added on both of those sides. So you would have this to be one of the sides, and that's actually going to be, that's this side right there. And then on the right side, you have only one carbon left, and that one carbon usually makes an formic acid first, but that's usually not very stable, so it's going to go away as a carbon dioxide. So remember that one carbon that you have there will go away as a carbon dioxide. If you had two carbons, then you would leave that as a carboxylic acid, but since you have only one carbon, it makes an formic acid first, but it's very unstable, so it goes away as a carbon dioxide. So that's what you really do in case of ozonolysis. Let's do the oxidation with potassium permanganate. Um, Now this one is also a little bit interesting depending on how you're really performing the reaction. You could do a couple of things. I could do a cold KMnO4 here. The cold KMnO4 makes syndiols. So I'm just having a copy here. So I would have both of those OHs either coming out of the page or going back in the page. So that would push this methyl going back in the page. So that would be one of your products. And obviously your second product, you could have these OHs going back in the page. And that would push this methyl coming out of the page. So that's actually goes ahead with so-called syn diols, where both of those diols will be either coming out of the page or going back into the page, but they both must be pointed on the same side. Then the second case scenario, what if you actually don't use cold KMNO4, but you use a concentrated KMNO4, something like you may see people writing it as a hot KMNO4 with H3O plus. So that goes through the formation of diols, but it actually goes ahead and open this ring and makes this product right there. I'm just going to go ahead and copy this down here. So it makes something very similar you would have actually seen in case of oxidative workup of ozonolysis. So that's what it's really going to make. It's going to put acid on the aldehydes once it breaks that bond. But if it's in a ketone, it will leave that in the form of a ketone. Another interesting fact that you would most likely see in this case is once you have these syn diols, I can actually go ahead and do one more reaction to these syndiols using maybe NaIO4. So some like periodic acid or periodate, and I can do oxidize these, and I will break this bond right there, and I'll oxidize those to make an aldehyde and a ketone. So that would be very similar to what we have seen in case of a reductive workup of from the ozonolysis. So that's what it's going to make at the end of the day. So it's important to know these reactions, but it's more important to know what the KMNO4 exactly really going to do when it's cold versus when it's concentrated. In case of an alkynes, we do something similar. If you have a cold KMNO4, or I would even say neutral, so if you have KMNO4 that's neutral and I would say like room temperature or cold, it end up making dicarbonyls. So that would look like this, okay? But then if you actually use a basic KMNO4 with an OH minus, so some sort of base along with it, it would go ahead and break the triple bond right there, and it will make carboxylates. So I would have the left side would make this, and the right side would have only one carbon left, so that will just go away as in a CO2, so we can just ignore that. And then obviously you can go ahead and protonate this. So when we protonate it, we usually use acid. Or you can also write it like this. In the first step, I'll use KMNO4 with an OH minus, and then I'll have in a second workup step with an H3O plus or with an acid, and that will end up making a carboxylic acid. So this is what you're gonna have the most common reactions that are gonna be going with both alkenes and alkynes in terms of additions. And keep in mind, you also do more addition reactions for alkenes that I didn't really talk about it here, but I just want to kind of mention what it happens when you just doing the addition reactions with common reagents that are used in alkenes and alkynes. If you have any questions, feel free to leave any comments in the section below.